Thank you, Dr. Draper. Today, I'm going to walk you through the procedure that we use to prepare our reference WNTs, long and short batches. Then I'll tell you about a few of the ways that we have physically characterized our reference WNTs. Finally, I'll discuss a few of our collaborations with other members of the Nanotox Consortium, as well as current projects in our own lab. So there are 5 basic steps to preparing reference WNTs. Seem to be having a bit of a problem with my pointer here. So to start off with, we use pristine WNT powder, which we purchase from Nano Amor. These WNTs have an inner diameter of 5 to 10 nanometers and an outer diameter of 10 to 20 nanometers. They are between 10 and 30 microns long and have a purity of over 95% according to the manufacturer. To disperse our WNTs, we use Poronic F108, which I will refer to as PF108. Poronics are triblock copolymers consisting of a hydrophilic polyethylene glycol block on either side of a hydrophobic polypropylene glycol block. PF108 has a molecular weight of 14,600 Dalton. But I'd like to point out that there are many different types of poronics with different size hydrophilic and hydrophobic block size. Dr. Nielsen's group at UT Dallas is using coarse-grained models to study the interaction of different poronic dispersants with WNTs. This will help us understand how to best choose poronic dispersants to disperse our WNTs. You can see here how the poronic forms a corona around the hydrophobic WNT. Now, returning to how we prepare our reference WNTs. We use ultrasound bath sonication to just exfoliate our WNTs, allowing them to be coated with PF108. We can vary sonication duration and power to produce long and short batches. We expect longer sonication or higher power sonication to lead to more WNT fragmentation and thus a final product containing shorter WNTs. We centrifuge our suspensions to remove non-dispersed aggregates as well as other impurities introduced by the manufacturing process. Finally, we dialyze against fresh PF108 to remove toxic sonolytic products. This is really important because, as we have previously presented, sonication of poronic actually leads to poronic degradation itself, which can be a primary source of toxicity. Now, I'm going to go into more details on our protocol, but first I want to stress that our entire procedure is done under sterile conditions. This ensures that our final products are compatible with in vitro cell culture assays. We start off with 10 mg of WNT powder, to which we add 10 milliliters of 0.2 millimolar PF108 solution. We give this solution a brief 5-minute sonication at a relatively low power of 72 watts. We then split our suspension into 2 5-mil aliquots. To 1 aliquot, we give it a quick centrifugation and collect the supername. We consider this supername our long WNT suspension. We expect these to be long WNTs because they only received a short, low-power sonication. Thus, there was less WNT fragmentation. From the other 5 mils from that initial sonication volume, we first bring it up to 10 mils by adding 5 mils of PF108. This ensures that we have a constant sonication volume of 10 milliliters. We then sonicate for 90 minutes at a high power of 120 watts. After 2 centrifugations, we retain the supernatant, which we consider our short WNT suspension. These WNTs we expect to be much shorter than the long WNTs because they receive much longer sonication at a higher power. For both of these batches, we've got 3 options after collection of the supernatant. As I previously mentioned, we can dialyze against PF108 to remove degraded PF108 fragments. This detoxifies toxicity that could be coming from those degradation products of the puronic, and also has the benefit that it ensures that you have a completely defined system, enabling accurate physical characterization. You don't have any puronic fragments floating around in your solution. Another option is to dialyze against another dispersant, such as BSA, to change the dispersant. Finally, if you're interested in agglomeration of WNTs, you can reduce the concentration of dispersants, also by dialysis, to induce such agglomeration. I want to stress that the long and short WNT suspensions come from the same starting material. They vary only in the amount, being the duration and the power of sonication. Now I'm going to discuss the way that we have characterized physically our reference WNT suspensions. We use dynamic light scattering to assess hydrodynamic particle size at strategic points in our procedure. DLS gives you a graph with percent intensity on the y-axis and a logarithmically scaled hydrodynamic particle size in nanometers on the x-axis. As you can see, the long WNTs, represented by the solid red line, and the short WNTs, being the dashed green line, have distinctly different profiles. The long WNTs clearly have a much larger presence than the short WNTs, represented by that shoulder there, that really large peak there. And correspondingly, the short WNTs have a shoulder descending into the small particle size that is not shared by the long WNT suspension. You can also calculate the average particle size using the area under the curves, which gives a 215 average hydrodynamic particle size for the long WNT suspension, whereas the short preparation yielded particles of only 120 nanometers hydrodynamic particle size. Now, it's difficult to correlate dynamic light scattering with length of our WNTs because hydrodynamic particle size isn't an accurate representation of WNT length. WNTs have a very high aspect ratio, so they can fold or bend easily when in solution, leading to an underrepresentation of hydrodynamic size compared to the actual length of the material. To accurately characterize our WNTs, we've collaborated with Drs. Yu Yang and Paul Westerhoff at Arizona State University to characterize the length of dry WNTs using transmission